Hello. In this problem, we are asked to look at a video which is mostly to show or have give you a physical insight into how styrofoam balls behave and what kind of forces we are talking. Often, when we are talking about electrostatic forces, we don't have a complete visual picture of what forces these are, and this gives you an example of uh, what kind of forces we are involved in. So it's closely or it's analogous to the magnetic forces we experience between magnets. And here, this is a case where we have electric forces in here. We have two styrofoam balls trapped inside a cylindrical plastic container. They are not in touch with the vertical walls of the cylinder itself, and that makes sure that there are no vertical forces on it. And even if and that's primarily because of symmetry, one can reasonably be sure that that happens. And we assume that there are no vertical forces in that sense. Let's label these balls as 1 and 2. Let me make this black. So this is 1 and 2. Let's say this is plus q here, and this is plus q. They're equally charged. Often they come and collide with each other. And if they're conducting styrofoam balls, which is easily achieved by coating them with aluminum foil, and then they experience an electric force. Suppose I were to draw this charge one separately here. So that's the ball separately being drawn here. They have a force mg acting downwards, relatively light, about 0.04 grams. That's typically the weight of the styrofoam balls, and of that order at least. And we have the electric force that has to balance this. That's what will let it levitate. And the electric force here is the Coulomb force, which will be K times Q square over the distance between them. That's the center to center distance. That's H square. If it's in static equilibrium, these two forces has to cancel each other, and that leaves us with a way to measure the charge Q. So the idea is there is no net force. That means acceleration is zero. So the forces has to balance. So Fe is equal to mg. These are equal and opposite. Sorry, these are equal charges, so they repel. So like charges repel. So it's k q square over h square equal to mg. You can plug in the numbers here at this stage. That's 8.99 into 10 raised to 9. Let's put in the units here because the equation is not uh, the equation can accommodate that. We try to avoid units to avoid clutter, but in this maybe we can put them in. So it is Newton meter square over Coulomb square. That's your unit for K. Q, that's what we are looking for, divided by H is 1 centimeter. So that's 1.0 into 10 raised to minus 2 to 2 sig digits. So it's meter square. Sorry, it's meters and then the whole square. Mg, it is 0.04, which can be written as 4.0 into 10 raised to minus 2, but then it's in grams. Converted to kg, that makes it 10 raised to minus 5 kgs. G, that's 9.8 meters per second square. All this leads to, see if I can grab this. How do I pull this down? Mouse. Ah, doesn't help much, so I have to make sure that stays intact. Okay, leaving the mouse, and we can come back to the pen, and I'll write the next step right in here. So, so charge square then, q square would be collect all the numbers. So that's 4.0. That's one way of proceeding. 4.0, 9.8. Bring down the 8.99. Should be one square also, but that's square is one. Getting all the powers together, I have 10 raised to minus 5. From this, there's 9.8, 10 raised to 1. So that's 10 raised to minus 4 coming from the power of the distance h. And this is 10 raised to 9. So that gives me 4 into 9.8 divided by 8.99. And I only needed to two sig digits because 9.8 has only two digits and 4.0 has only two sig digits. So that's 4.4 into 10 raised to minus 9 in the numerator, 9 in the denominator, plus 10 raised to 18. What's the units? Meter square cancels here. Kg meters per second square is Newton. Newton cancels that, so we're left out with a Coulomb square, which is nice because charge is measured in coulombs, so there's Coulomb square, so the units balance out. Take the square root on both sides, and we get charge Q is equal to square root of 4.4, and that's 2.1 into 10 raised to, oh, this should be minus 18, sorry. That's 10 raised to minus 9 coulombs, which is 2.1 nanocoulombs. And that's the scale in which these charges work. Usually, the charges we encounter on a daily basis is in the regime of microcoulomb to nanocoulomb. Nanocoulomb is somewhere about 10 nanocoulombs is what we encounter when we are doing when we are going experiencing static electricity. Anything beyond a microcoulomb is typically a large amount of charge. And that brings the problem to an end. So let me stop the recording.